Our Glory Globe TVers breaking news. Yes, a new study led by researchers from UCL and come to Imperial College London has brought us one step closer to form a brain-inspired computing that exploits the intrinsic physical properties of a material to dramatically reduce energy use. In the new study published in the journal Natural Materials, an international team of researchers used Chiral twisted magnets as rare computational medium and found that by applying an external magnetic field and changing temperatures, the physical properties of this material could be adapted to suit different machine learning tasks, such as also called the such an approach known as physical reservoir computing has until now been limited due to its lack of reconfigurability. This is because a material's physical properties may allow it to excel at a certain subset of computing tasks but not others. Dr. Oscar Lee at UCL and UCL Department of Electronic and Electrical Engineering, the lead author of the paper, said, "This work brings us a step closer to realizing the full potential of physical reservoirs to create computers that not only require significantly less energy but also adapt their computational properties to perform optimally across various tasks, just like our brains." The next step is to identify materials and device architecture that are commercially viable and scalable. Traditional computing consumes large amounts of electricity. This is partly because it has separate units for data storage and processing, meaning information has to be shuffled constantly between the two, wasting energy and producing heat. This is particularly a problem for machine learning, which requires vast data sets for processing. Training one large AI model can generate hundreds of tons of carbon dioxide. Physical reservoir computing is one of several neuromorphic or brain-inspired approaches that aim to remove the need for distinct memory and processing units, facilitating more efficient ways to process data, in addition to being a more sustainable alternative to conventional computing. Physical reservoir computing could be integrated into existing circuitry to provide additional capabilities that are also energy efficient. In the study involving researchers in Japan and Germany, the team used a vector network analyzer to determine the energy absorption of chiral magnets at different magnetic field strengths and temperatures ranging from minus 269 degrees Celsius to room temperature. They found that different magnetic phases of chiral magnets excelled at different types of computing tasks. The Skyrmiron phase, where magnetized particles are swirling in a vortex-like proton, had a potent memory capacity apt for forecasting tasks. The conical phase, meanwhile, had little memory, but its non-linearity was ideal for transformation tasks and classification, for instance, identifying if an animal is a cat or dog. Co-author Dr. Jack of Imperial College London said, "Our collaborators at UCL in the group of Professor Kurobashi recently identified a promising set of material for powering unconventional computing. These materials are special as they can support an especially rich and varied range of magnetic textures." Working with the late author Dr. Oscar Lee, the Imperial College London group, Kellen Stenick and Professor Will Bernborn designed a neuromorphic computing architecture to leverage the complex material properties to match the demands of a diverse set of challenging tasks. This gave great result and showed how reconfiguring physical phases can directly tailor neuromorphic computing performance. Bravo! BN Desi Glory Globe TV, Delhi, Bharat.